Okay. Welcome everyone to our seminar, Statistical Quantum and Classical Statistical Physics. That's the first seminar in the new year, and we are very pleased to have Gregory Schehr with us for the first talk in this year. So he's did his postdoctoral degree at Saarland University in Germany, and nowadays he's permanent researcher at the Laboratory for Theoretical Physics and Statistical Models at the University Paris-Saclay. And his research lines are extreme value statistics, non-equilibrium dynamics, first passage problems, and disordered systems. His talk will be about, well, the title of his talk is Random Matrices Meet Trapped Fermions. And okay, we are very happy to have you here. Welcome. And let's now start with the talk. If you are in the meeting, you may ask questions at any time. Just give notice via the chat. For those on YouTube, you may also leave questions in the comment section, and we will ask these questions then to Gregory at the end of the presentation. So looking forward for the talk. I pass you the word, Gregory, please.
Okay. Thank you very much for the introduction. Thank you very much also for the invitation. I'm very glad to have this opportunity to talk to you, even though, of course, I would have been very happy to do that in person. But at least this gives us the opportunity to interact and talk about science across the oceans. Today I would like to give you a sort of overview of the work that we have been doing during the last, say, 5-6 years around this topic at the interface between random matrices and trapped fermions. So as I said, this is a relatively long-term project, and my main collaborators actually have been during these years, my collaborators and friends, I should say, David Dean from Bordeaux, Pierre Ledoussal from École Normale in Paris, and Satya Majumdar in Orsay from LPTMS. Of course, many PhD students and postdocs have also contributed to this topic, and we'll have the opportunity to cite their work during this talk. To start with, I just wanted to mention that we wrote 2 reviews on this subject, one in PhysRev A and another in GPhys A, which you can also find easily on arXiv. So one of the motivation for this work comes to some extent from experiments. As you know, there have been tremendous progress in the manipulations of cold atoms, either bosons or fermions, and this allows to investigate in a rather detailed way the interplay between quantum and thermal fluctuations in many body systems at low temperature. And in fact, a common feature of all these experiments is that if you really want to observe and make some measurements on your particles, well, you need them to stay in a confined region of space, and to do that, you typically realize a trap, or typically an optical trap, which is usually described by a potential, say in one dimension here, V of x, and that allows you to keep your atoms in a limited spatial region. Now, another, kind of experimental challenge that our colleagues have been able to realize during the last years is that it is now possible to really take a picture of these cold atoms, gases, and in particular, since I will mainly discuss fermions in the following, I wanted to show you this kind of snapshots, which is taken thanks to what is called quantum Fermi gas microscopes, So this is a direct imaging of the positions of your fermions. So this is a picture that was realized in the group of Marcus Greiner at Harvard on these experiments on lithium-6. And they were really able, if you see, so 1 pixel here is basically the position of one atom. And it's quite natural then to ask what can be said about the statistics of these points here. Do they look like a Poisson point process? Do they look like a determinantal point process? Do they look like to some other types of random point processes? And is it possible to say something about the fluctuations of these point-like configurations? On top of that, it turns out that it is also now possible to tune the interactions essentially at will. And eventually, this allows, thanks to the use of what is called Feshbach resonance, it's even possible to reach the non-interacting limit. So that means that you can essentially consider that you deal with quantum particles, say fermions, but which are non-interacting. And this is, in fact, extremely interesting because it allows really to study the pure quantum many-body effects on these particles. And as we know, even in the case of in the absence of interactions, it turns out that these cold atoms, cold atomic gases, they actually exhibit very rich collective phenomena. If I talk about bosons, of course, one should have in mind Bose-Einstein condensation. But since we are talking about fermions today, we should have in mind that, of course, these particles, they experience the Pauli exclusion principle, and effectively, they experience a kind of repulsive interactions. And as we will see, and as we already know to some extent, this actually leads to a rich quantum many-body physics. Now, of course, this kind of problems, that means fermions in a trap, or say non-interacting fermions in particular, they have been extensively studied in the past. And in fact, it turns out that although they have been extensively studied, what is known is basically what happens in what I would like to call in the following the bulk. That means that when you confine your atoms, say your fermions, in a trap here, what happens is that because of the competition between the confining potential that would like to have all the particles in the center and the Pauli exclusion principle, which is instead a repulsive interaction, it turns out that the density of particles has a finite support. That means that beyond a certain scale, the particle density essentially vanishes. It's identically zero. And that means that there is a kind of edge. That's what I will call, that's how I will call this region later. And contrary to the edge, I would like to call this region the bulk. That means the region which is close to the center of the trap and therefore quite far from the edge of the density. And in fact, if you are close to the center of the trap, what happens is that to a large extent, you can essentially forget about the curvature of this potential. And that means that you have a problem which is basically translationally invariant. And to treat such systems, actually, they have many standard treatment and standard tools to do that. On the other hand, if you want to study what happens at the edge, the situation actually is much more complicated. The first thing to notice is indeed that because of the edge, you break the translational invariance. And there, in these regions, of course, you start to experience the curvature, and we will be more precise about that in a minute. And another aspect is that typically, when you are close to the edge, the density of particles, the density of fermions, as you would expect, is actually the density is actually much smaller, okay? And that means that this is a region which is also much more sensitive to fluctuations, either quantum fluctuations or thermal ones, as we will see later. And it has been recognized already some time back in a very nice paper by Walter Kohn, the chemist, Nobel Prize, and Madsen, in this very nice PRL, where he writes actually that the uniform electron gas, the traditional starting point for density-based many-body theories of inhomogeneous system, is inappropriate near electronic edges. And that clearly raises the question of how to deal with what happens near the edge. What can be said there? Are there any interesting universal properties that can be studied? And to answer these questions, it turns out that one really needs to develop new techniques. And what we have actually realized and discovered during these last 5-6 years with my colleagues is that it turned out that random matrix theory is an ideal tool to study these properties. Okay, so, and in particular, as we will see, it turns out that using these techniques, one can show that there is very interesting new physics induced by the confinement. And in particular, we will see that it turns out that the properties near the edges are actually to a large extent universal. That means that they are to a large extent independent of the type of trapping potentials. And as we will see, at least in one dimension, they share many common properties with random matrix theory. So that's a bit the motivation of this work. And to be more precise, let's consider the case of a one-dimensional system where you have fermions in a harmonic potential. And in fact, and that was one of our motivation, the first motivation for the first work that we did on these fermions, is that if you look at the ground state of this system, one can show that there is a direct correspondence, a direct and exact mapping between spinless fermions in a harmonic trap and random matrix theory. And it turns out that there is a direct connection with the so-called Gaussian unitary ensemble, and that was actually one of the first properties that drove us to study more this system. In particular, because we had already some expertise in random matrix theory, and we wanted to somehow import these techniques and tools to study these fermion problems. So that will be essentially the first part of my talk. I will just show you or remind maybe for some of you the connection that exists in D=1 between random matrix theory and free fermions at 0 temperature. And then I will go to the finite temperature case, which of course is more relevant somehow to experiments. And there I will show you a very, very intriguing connection to stochastic growth models, namely the Kardar-Parisi-Zhang equation, which to some extent was one of the main results probably that we had at that time when we started. And then I will try to show you, I mean, if I have time, I will try to show you some nice extensions in higher dimensions. And then if I have more time, I will just try to show you some outlook and perspectives on this work. So let's move on and let's look at this textbook exercise, textbook problem of a single quantum particle in a harmonic potential. Okay, so this is my Hamiltonian, and as you well know, the single particle eigenfunctions, they are actually labeled by an integer, which I will call k, and the energy levels are simply this h bar omega k plus half. And now let's look at the structure of the wave functions. So the wave functions actually are the product of a Gaussian term, okay, and a polynomial which depends on k, and which are simply the Hermite polynomials. Okay, so this is a well-known problem in quantum mechanics, one of the first one that one solves when we learn the Schrödinger equation. Now, of course, at this stage, there is a single particle, so there is no bosons or fermions. I'm just looking at one particle. But now let's try to see how one can construct the ground state of spinless fermions. Say you take n fermions and you forget about the spins. So, I mean, what it means is that you imagine that you just polarize all the spins in the same spin states, namely either all the up spins or down spins, so that you can essentially forget about the spin component of the wave function and simply focus on the spatial part of the wave function. So the way to do that, because they are fermions, of course, you can just occupy one level by a single fermion. So you start by occupying the ground state, k equal to 0. And then you put, when comes the second fermions, you put them in a k equals 1. And then the third one in a k equals 2, and so on and so forth. And you do that until you have basically piled up your n fermions. So that's quite simple. Now, on the other hand, you know that because you have fermions, the many-modi wave function has to be totally anti-symmetric with respect to any permutation of any two particles. And the standard way to do that is to construct what is called the Slater determinants. That means that you just write that your wave function, ground state wave function, psi 0, x1 of x2, xn, is just the determinant of the single particle wave functions. And therefore, it's totally anti-symmetric. And obviously, this also satisfies the Schrödinger equations. Now, there is this 1 over square root of factorial n, simply by normalization. So let's try to see what this determinant is, and let's try to manipulate it a little bit. So if I look at this determinant, okay, the ground state energy, which will not play any role here. So you see, if I look at this determinant, I can, by simply using the multilinearity of the determinant, I can just get out these Gaussian factors here. So that means that the psi 0 will just be basically the product of these Gaussians times the determinant of these polynomials. Now, if you remember a little bit of a standard course in linear algebra, you would remember that by manipulating the rows and columns of such determinants with polynomial entries, you are able actually to write this determinant of Hermite polynomials as a van der Monde determinant. Okay, so that's quite standard exercise in linear algebra, and that's what you get. And maybe just one remark for those of you who already know a bit of random matrix theory. Usually in RMT we do the other way around. So we start with a van der Monde, and we say that it's actually possible to write this van der Monde determinant in terms of a determinant with polynomial entries. And usually it's quite useful to choose these polynomials to be the orthogonal polynomials with respect to that measure, the Gaussian measure. And for the Gaussian unitary ensemble, this turns out to be the Hermite polynomials. Okay. Now in quantum mechanics, I mean, this is more the other way around. That's at least what I want to do. And so you have this nice structure here. Of course, there is a prefactor here that I've not taken into account, but which you can always fix at the end of the day by normalization. So this is psi naught, but of course we know that the physical observable is the probability density function associated to the positions of the fermions. And this one is given by the modulus square of psi 0. And if you just take the square of it, then that's what you get. So you get this product of the Gaussians here, and you have this nice determinant squared here. Now it's quite nice to see this term here, because you see, I mean, it really comes from the Fermi, the Pauli exclusion principle, right? That says that if xi is equal to xj, then this wave function will, of course, vanish. So you have an effective repulsion, which is indeed related to the Pauli exclusion principle. Now, what is interesting about this joint probability density function is that this is exactly, it turns out that this is exactly the same as the one that one encounters in random matrix theory. Indeed, if you take a Hermitian matrix, call it J, which is of size n by n, and you just fill it with random entries, both the real and complex part, with Gaussian entries. And it's well known since Dysons and Wigner, essentially, that one can actually compute the joint probability density function of the real eigenvalues of lambda i's. Of course, because your matrix is Hermitian, all the eigenvalues turn out to be real. But because your matrix J is random, of course, the eigenvalues of this matrix are also random. Okay. And the natural question to ask is, what is the distribution of these eigenvalues? And it's well known that it takes actually this nice expression here. But now you see that if you really compare these two expressions here, well, you see that they are essentially the same up to rescaling of the positions xi. So in other words, if you look at alpha times xi, they actually behave as the eigenvalues of RMT. And you see, it's really an exact mapping. That's actually exact for any n equals 2, 3, 4. And that allows you essentially to import all the knowledge that you have from random matrix theory to study free fermions, or say free. By free, I mean non-interacting fermions, I should say, non-interacting fermions in the presence of harmonic trap. Right, so just a single word about this, maybe for those of you who like RMT. It turns out that it's actually possible to realize the other classical random matrix ensemble, the unitary ones, by specifying correctly the potential that you take in your Schrödinger Hamiltonian. So for instance, the Laguerre ensemble can be chosen by, instead of having only a quadratic term, then you add this 1 over x squared potential, which you can roughly understand as a kind of repulsion if you have, for instance, a wall at x equal to 0. And in this case, you get the Laguerre ensemble. Another classical ensemble is the one which is called the Jacobi. I will not comment too much on that, but in fact, the Jacobi ensemble can be straightforwardly realized by a simple outbox potential. You just take your particles between -1 and +1, and basically you will find that the ground state of this system is connected to the Jacobi unitary ensemble. And that was actually part of the thesis of my PhD student, Bertrand Lacroix-Chétoine. And that means that all the knowledge that you have from RMT can be imported to study free fermions. And so let's come back to the GUE ensemble. Okay, so I just come back to the quadratic, say harmonic trap. These connections actually has been widely studied by various people and groups during the last years. I mean, okay, the list is actually far from being exhaustive. So let's see what kind of information one can extract from it. Before that, I should just be sure that the audience is with me. I mean, everyone can hear me and see my screen properly. The rhythm is okay.
Yes, I would. Well, I think yes.
Okay.
Nice.
Fine. So the first thing that you should know and that we can import directly is related to the density. Okay, so you would like to know something about the density of free fermions, and that means that it's equivalent, because of this connection, it's equivalent to know the density of the eigenvalues of a Gaussian unitary ensemble in the Gaussian unitary ensemble. And it's known to take this famous Wigner semicircle law. So let's just mention something first about the scale. So what you will see is that the typical scale is square root of n. So that means that the density or the support has a range which is typically over the square root of n. And inside this support, it takes this Wigner semicircle law. Okay, so it has actually this shape here. And that tells you, roughly speaking, that you have all the particles, if you want, they are inside this support, minus square root of 2n plus square root of 2n. Of course, this is only valid in a large n limit. And within this approximation, you would see that basically the density is exactly 0 outside. Of course, for finite n, this is not true, and we will come back to that in a minute. But this is also, so this is a classical result in random matrix theory. This is also well known, actually, in the literature on fermions, and this corresponds to what is known under the name of the local density approximation, or Thomas Fermi approximation, which you have maybe heard about. So that's quite nice, but it's also quite interesting to have in mind that because of this finite, because of this the shape of this Wigner semicircle law, and because you have a finite support, it turns out that, as I said before, that you have two typical scaling regimes. One, which I would like to call the bulk, as I did before, which is essentially quite far from the edge. Okay, so for me here, the edges are just this point here where the density vanishes. Okay, so this is square root of 2n divided by alpha and minus the same quantity because the potential is symmetric. So if you are very far away from these edges, well, the density in the bulk is basically uniform. I mean, it's close to uniform. I mean, if you are close to the very close to the boundary, to the center, sorry, of the trap, and it's relatively easy to estimate the typical distance between two particles, right? Because you see, you have n particles, and they are distributed over an interval which has size of order square root of n. So the typical distance between particles are square root of n divided by n, which is 1 over square root n. And there, it's well known that you get basically the bulk regime, and I will come to that later on when we will discuss more refined properties. Now, on the other hand, at the edge, you would like to estimate the interparticle distance. As I said, you would expect that the density is actually lower simply because the density is going to vanish exactly there. So that means that the number of particles here should be very, I mean, you only have a few particles. Now, how can I estimate the interparticle distance there? Well, I can use a standard argument, which is often used actually in extreme value statistics, which is basically what is written in the last line here. So what I will say here is that if I want to estimate this length, which I call L edge, which is the interparticle distance at the edge, then I will roughly say that the number of particles on this interval, that means between R edge, so R edge is exactly this square root of 2n divided by alpha, and R edge minus L edge, so the number of particles in this interval here, so that means n times this integral here, should be of order 1. Okay, that tells you that there is typically 1 particles in that scale. And if you do that, so that tells you that this integral of the density over this interval should be of order 1 over n. Now, because the density vanishes as a square root, this gives you, so you really need to do the algebra. This is straightforward, but this needs to be written down. What you find is that this typical length here scale like n to the power minus 1 over 6. Okay, so that means this is much larger. The distance here is much larger than what happens in the past. Fine. So now you would like to know more about what happens at the edge. Okay, I mean, I said, okay, we know we have here a rough estimate of the mean particle spacing, but you would like to say to understand what happens about the density. And in particular, as I said, when n will be large but finite, of course, the density on the right side here will not be exactly 0. Okay, there will be a tail there that you would like eventually to describe. So the question is what happens there? And that's really where the standard theory for fermions fails, and that's what Walter Kohn had in mind when he wrote that. Now, hopefully, it turns out that that's what I'm writing here, that random matrix theory comes to the rescue, because it turns out that in the last 20 or 30 years, it turns out that the edge properties in the context of random matrices have actually been widely studied. And we will use basically this knowledge to understand better what happens for fermions. And actually, the first results on that is due to Marc Bovic and Edouard Brezin in 91, and later on by Peter Forrester in 93, where they were able to derive the density profile close to the edge. Okay, and this has this form here. So it takes place on a width which is of order Wn. So this is the n to the power minus 1 over 6 that we have seen. And it's described by this airy function type. And this has this behavior here. Okay. So let's first look at what happens on the left here. So if I look at what happens on the left, you see when z is very small and I mean negative and large in absolute value, this actually, you have some oscillations, but this is growing like square root of z. And what you need to have in mind, what you really have to have in mind is that this will actually match with the Wigner semicircle. Okay, so that's the square root of the Wigner semicircle, which would basically vanish like that here. Okay, so we would have this square root behavior plus some oscillations. Now, on the other hand, if you look at what happens on the right-hand side, where the standard theory would predict simply 0, what you see is that there is a non-trivial tail, which is this exponential of minus z to the power 3 by 2. And maybe I will come to that later on, but this is really the tail governed by these airy functions. Then. So that's nice. We have now quite a nice description of what happens for, say, the density, so 1-point quantities. Now, of course, we would like to know more, and we would like to be able to compute higher order correlations, for instance, 2-point functions. Okay, that would be the kind of correlation function that you would like to study. And from the point of view of fermions, this is something which is relatively easy to compute. For instance, you would like to compute the n-point correlation function, which is obtained from the n-particle ground state wave function by integrating over the xn plus 1 to x capital N. Okay. Now you can then use the properties that you know from random matrix theory, which is that the process that we are looking at, that means either the positions of the fermions in the Gaussian unitary ensemble, or the eigenvalues, either the positions of the fermions in a harmonic potential, or the eigenvalues in the Gaussian unitary ensemble, they actually form what is called the determinantal point process, which means that any n-point correlation of this type here can be expressed as an n by n determinant. So that means that this guy here, we can just write it as an n by n. So n is the index, is not the number of fermions, right? Small n here is just the number of points that you want to have. So the 4-point correlation function would be a 4 by 4 determinant. And the size of the system only, that means the number of fermions only enters into this quantity, Kn. And this Kn this is what is called the kernel. Okay. And it has an explicit expression in terms of the single particle wave function, which in the case of the harmonic potential would be simply the Hermite function. And so in particular, you can just get the average density. Now, this determinantal structure is well known in the context of RMT, and people like to talk about, or at least people like me, like to talk about this determinantal point process. Now, in fact, in the context of condensed matter, this is just the exact analog of what is called as the Wick's theorem. Okay, and the Wick's theorem for non-interacting fermions tells you indeed that you can compute the n-point correlation function in terms of what is called the kernel, which is basically a 2-point correlation function, and which is basically this psi dagger x psi y in the second quantification language. Just to make a connection with some knowledge that you may have on fermions. This is not just coming out of the blue, right? Okay. Now, so that means that if you want to understand the correlations of your gas, you need to understand what happens for this kernel here. Now, as I said, we have seen that there are two regions, right? One which is in the bulk, and the other one which is at the edge. So let's look at the structure of the correlation kernel when you are close to the center of the trap. So that means when the particles are very close, so on the order of the interparticle distance. And if you are in the bulk, this kernel here actually takes this very well-known form, which is known under the sign kernel, which has this sign cardinal form here, which is well known in RMT, and I'm sure you have seen it. Before. Now, if you look at the edge, the things are actually much more complicated, and in particular, what you see now is that it has an expression, quite non-trivial expression in terms of airy function. This is known under the name of airy kernel, and in particular, you see that this kernel here, if I look at what happens in the bulk, you see the kernel depends only on the relative distance between x and y, and this is because locally your system is just translationally invariant. This is not at all the case at the edge, where you see that your kernel, the airy kernel, actually depends both on A and B, and not only on the difference A minus B. Okay, and that actually renders the things much more complicated. But nevertheless, it has been, widely studied in the context of RMT, and in particular, if you want to probe the edge properties of your fermions, I mean, since this is what we are after, right? We want to characterize what happens at the edge of this Fermi gas. Well, a natural quantity is just to look at the position of the rightmost fermion. Okay, so that means that you take a snapshot of your Fermi gas, and you look at the position of the rightmost fermion, and then you repeat the experiments. Okay, so this guy will fluctuate from one snapshot to another, and you may like to understand the statistics of this rightmost fermion. Now, of course, in the large n limit, the rightmost fermion will be very close to the edge here. Okay, so the zeroth order answer is just that x max is basically distributed as a delta function at square root of 2n divided by alpha. But of course, you would expect some fluctuations around that. And again, these fluctuations, you already know the scale of it because we have estimated, we have seen that the typical length scale is this 1 over n to the power minus 1 over 6. So that will be the typical scale of the fluctuations for this guy, for this rightmost one. Now you would like to know more. You would like to ask, okay, but what are the distribution of this guy, of these fluctuations? Are there Gaussians? Are there exponentials? Are there algebraic, whatever? What kind of distribution should I expect? Now it turns out that because of the connection with random matrix theory, this x max here is nothing else, up to rescaling, is nothing else but the largest eigenvalue of random matrices in a Gaussian unitary ensemble. And as you probably know, this has actually been widely studied during the last 20 years. And in particular, it is well known that the fluctuations of this quantity are governed by what is well known under the name of the Tracy-Widom distribution, the two gentlemen who discovered this distribution. And this distribution is actually quite, I mean, it has a rather complicated expression. You can actually write it as a Fredholm determinant. So it's a kind of functional determinant. I will not enter too much into the details, but it has this structure here is the determinant of the identity minus something which you can express in terms of the kernel that we have seen before, which is this area kernel. Okay, so either you know what it is, and that's fine, either you don't know, and that's also fine, because you just need to remember that this can be built as a determinant constructed from this operator, which is this area kernel. Now, as I said, this Tracy-Widom distribution has been widely studied during the last 10 years, and in fact, what is 10 years? In fact, I should say 25 years. It turns out that the very same distribution has appeared in various problems, ranging from the Kardar-Parisi-Zhang equation, directed polymers in random media, some problem in combinatorics, like the longest increasing subsequence of random permutations, or like sequence alignment problems, and so on and so forth. Now, it's quite nice to notice that at the end, all these systems, I mean, are quite complicated, but somehow these free fermions, these non-interacting fermions in a quadratic potential, is probably one of the simplest physical systems where this Tracy-Widom distribution could be observed. So that's a quite remarkable fact. And something that I will not probably comment on too much, but which I should comment on at this stage, is that although we have done only the calculations explicitly for the quadratic potential, what we can show is that what happens at the edge are completely universal. That means that they do not depend on the precise shape of your potential, provided it has some smoothness properties. But for instance, if you take x to the power 4 or x to the power whatever, some polynomial expansion or some polynomial form which is quite smooth, then in all the cases, you will, if you look at what happened at the edge, you will again find these airy types of kernel and this Tracy-Widom sort of distribution. So that's why we believe it's quite interesting, because it's in fact universal, and this is something that probably should be observable, at least in experiments. Now, of course, as soon as you start to talk about experiments, you might wonder whether you are really at zero temperature, or whether thermal effects might be important. So let's see what happens at finite temperature. Now, of course, the situation at finite temperature is much more complicated for the following reason that one can pictorially see. If I am at t equals 0, you see I just populate the n first eigenstates. So that's quite easy. But as soon as you put
Gregory?
some... Oh, yes. Yes.
Thomas have a question.
Yeah, please.
So just please, maybe before you start with the finite temperature, because
Oh,
somewhere in the beginning you mentioned that the curvature is important at the edge.
yes.
Can you comment a little bit on that? So is it the curvature which
Right.
shapes the distribution of the largest, or is it the... I would
Yeah.
have thought that it's just a derivative. So
Yeah, so indeed, I mean, so what, yeah, so yeah, absolutely. So what I wanted to say, but by the fact that the curvature becomes important is just that the density really at this stage, I mean, at this the density at this point here really vanishes. And that means that if you naively take this, okay, if I take this formula here, which is valid in the bulk, okay, I am really, if I really look at what happens at the edge, well, this rho n here is really 0. Okay, so that means that this scale here, this small l here, is virtually, I mean, is just diverging. Okay, and that means that conceptually, I mean, there is clearly a problem there that signals the fact that you cannot use the bulk approximation. And of course, the reason behind that is that you have, because of the potential, you have created an edge, and that's what I meant by the importance of the curvature.
okay, thanks.
But then to go a bit beyond and answer a bit more precisely what you said, if I look at what happens here, basically the type of potential that you will have. Oops, sorry. So if I change, instead of having the quadratic potential, the dependence on the potential will actually lies, of course, our edge itself will depend on the potential, but more importantly, Wn will depend. Okay?
Okay, yes.
So all the dependence on the potential will be captured in this Wn. And so in fact, it might be even that the scaling with n will be different.
Can I ask, is it local? I mean, do the local properties define the distribution? The local
Yes.
properties are in the edge, or is it the
absolutely.
global form of the potential?
Yeah, no, you're right. So okay, and maybe I can even be more precise to the first question that and I think that's what you had in mind. The way you can see how this area function comes in is precisely that the naive way to obtain them is just to look at the Schrödinger equation and try to solve it close to the turning point, so close to the edge. And close to this edge, of course, you will just linearize your potential. And that means that the first derivative of the potential basically will play a role. And that's what will give rise to this area function, okay? Because you will solve the essentially the Schrödinger equation in a linear potential, and that you will get the area function.
Okay, yes.
Did I answer your question?
Yes, thanks. Yes.
Okay. So that's why also, of course, you see that you need some smoothness properties of the potential to do that. Okay, so if you have typically a hard edge type of things, then you wouldn't be able to do this kind of imagine that your potential is really diverging at some point. Then of course you would enter in some other universality class, which might be the Bessel kernel, for instance, or the hard edge kernel in the language of RMT. But provided you can do this linearization that you have in mind, then you will really have the area kernel as a limiting distribution. So it's quite local indeed. Okay. So let's try to come back to finite temperature. Yeah, I'm running a bit out of time actually. I mean, I can see, but okay, I will just stop whenever.
Don't worry, it's not.
Okay. So again, at zero temperature, I think we have all understood now how it works. We just pile up these n first sets. Now, as soon as you start to increase the temperature, of course, the states that will be allowed, of course, are much more complicated because you will be able essentially to create some hole in the Fermi sea, and you will have some excitations above this Fermi energy, right? Which is the last level, which is occupied at 0 temperature. So that means that in principle, when you write the wave function, well, then it has a much more complicated form. Okay, so it's a complicated sum, and it's a sum over all the possible states that you can have. So the states are just labeled by K1, K2, Kn. So these are the states which are occupied. So here, for instance, that would be K1 is equal to 1, K2 is equal to n-1, K3 is equal to n, and so on and so forth. Now you have n such states, K1, K2, Kn, and the associated wave function is just the Slater determinant squared. But of course, we are at finite temperature, so you have to pay a price for creating these excitations, and that means that they will only appear with a probability which is proportional to the Boltzmann weight, which is simply the exponential of minus beta times the sum of the energies of these states there. And of course, you have some, in front of that, you will get some normalization constant, which I do not care so much. But the very fact is that you, instead of having a single Slater determinant square here, which we could handle relatively easily, now the situation becomes much more complicated because now I have an infinite number of determinant square, and this is much more complicated to handle. And in fact, it turns out that analyzing precisely this quantity here in the large n limit turns out to be quite complicated because it says, in fact, that we have lost somehow the determinantal structure in the canonical ensemble. Okay, so here you see I'm looking at the problem at finite temperature in the canonical ensemble, which is something which could seem rather natural from StatMech point of view. But on the other hand, from the quantum mechanics point of view, we know that as soon as we are dealing with fermions or bosons at finite temperature, it's usually much more convenient to work instead in the grand-canonical ensemble. And that's what we would like to do here. But before that, let's try to understand a little bit the relevant length scales at finite temperature. And let's try to understand, in which temperature range we expect to see temperature to be important and quantum fluctuations to be of the same order as thermal fluctuations. So to do that, let me just recall the two length scales that we had at 0 temperature. Okay, so we had the bulk. In the bulk, we had this 1 over square root of n. And at the edge, we had this 1 over n to the power 1/6. Now, when you introduce temperature, you have an additional length scale, which is simply the de Broglie wavelength. Okay, and the de Broglie wavelength is proportional to h Planck constant divided by square root of t, and we know that this is this length that basically controls the crossover from quantum to classical physics as temperature increases. Okay, so let's see what it means in the bulk. Well, basically, we know that the system will behave in a quantum way if the Broglie wavelength is much bigger compared to the typical length between two particles. Okay, because that means that basically the extension of the wave function is much bigger than the typical length between two particles, and therefore you will see some quantum interference dominating. And if you just plug the expression for lambda t and for this L bulk there, you see that the KBT, so that means that quantum fluctuation will dominate as soon as KBT is less than h bar omega n. Okay, so t has to be compared with n. And instead of that, the system will essentially behave classically if lambda t is much less than this length. And so the crossover temperature is basically n here. Now, on the other hand, if you look at what happens at the edge, the things are different, of course, because the scaling with n of these lengths is quite different. Okay, and we know that this length here is much larger. And in other words, if you do the same kind of argument there, what you see is that in fact, the system will be will remain quantum as soon as t, provided t is less than n to the power 1/3, and on the other hand, it will behave classically if t exceeds this length. This scale here. So you see that the typical, in terms of n, again, I have in mind the harmonic potential, but most of these things actually can be translated to into any potential. You see that the typical energy scale in the bulk is t proportional to n, while at the edge is t to the power n to the 1/3. Okay, so that's t proportional to n to the 1/3. Fine. So this is, of course, very rough, and you would like to go beyond. Now, as I said, to go beyond, we need to forget about the canonical ensemble, where the particle, the number of particles n is fixed, and we just need to go to the grand-canonical ensemble. And in fact, where the chemical potential now is fixed. And now you would expect indeed that in the large n limit, at least if you look at the local correlations, what you can show is that for large n, the local correlations that you will compute in the canonical actually coincide with the one that you compute in a grand-canonical ensemble at leading order for large n. One should, however, be careful with such equivalence. And in fact, if you look at global quantities, it might not be the case. So this is correct if you look at local ones, like the kernel, correlation kernel, like the fluctuations of the largest rightmost particle, which I will look at in a few minutes. But if you start to look at some global properties, this is something that you should consider with care. And we have studied that in one of these papers with Aurélien Grabsch, who was PhD student with us. So what is nice now, is that in the grand-canonical ensemble, the system is again a determinantal point process. And in fact, you can actually compute the kernel in an easy way. So that suggests that for large n, even if you are working in the canonical ensemble, well, basically in the large n limit, your system resembles to a determinantal point process at leading order for large n, and the kernel is basically written there. So it's just the sum of the phi kx prime, but now you multiply by a factor, which is just the Fermi factor. Okay, so that's now the kernel which you have to work with. But what is nice is that, as I said, you have a determinantal point process, so many things can be computed. So you can use what you know for determinantal point process and say something about that. So I will not focus too much on what happens in the bulk, but directly give you the results that we have obtained if you look at what happens in the edge. Now, as I said, at the edge, we have seen that to see something, we need to have t over the n to the power 1/3. If t is much less than that, basically, we will recover the zero temperature physics that I showed to you. And if t is much larger than that, we will simply have classical physics of non-interacting particles in a harmonic well, which is quite boring. But on the other hand, if you scale t like that, then you will see a very nice crossover from basically quantum to classical behavior. So let's first look at the density. Well, first, the thing is that if you look at the density, the global density will remain unchanged because t is still very, if it is like n to the 1/3, it is still much less than n, and therefore the global, the bulk physics is unchanged, and it is still given by the Wigner semicircle. On the other hand, you would expect that things become different if you look at the edge, and this is indeed the case. And you can actually, it's actually quite possible to look at what happens close to the edge. And you will see that a bit as we had before, you can actually compute the density profile. It's now given by this airy kernel, but modulated by this Fermi factor. Okay, it has a very nice and simple expression. And this is a plot of this profile. This is the zero temperature limit, where you see one sees some quite nice oscillations. And now, as temperature gets higher and higher, well, as you would expect, you start to see these less and less oscillations. And eventually, temperature is quite high, so B is small. B is 1/t, essentially. you stop. I mean, basically, you don't see these oscillations anymore. So that's for the density profile. Now you can go beyond again and look at the higher point correlations. So again, we have a determinantal point process. So all the correlation functions, they will be given by a kernel, and this kernel now is different. I mean, is not anymore the array kernel, but it's actually given by a generalization of the array kernel, which is basically the product of this array function, but again modulated by this Fermi factor. Now it turns out that in math, in probability, this was discovered by Kurt Johansen in a completely different context. I mean, not really in the Fermions, and I will maybe come back to that in a minute. But what is nice is that now we can even compute what happens to the rightmost Fermions. Again, maybe one aspect that I want to maybe repeat is that everything that we have here at the edge is completely universal, and it's actually quite independent of the confining potential. So this form here will, again, the scaling form here will hold actually for a wide family of potentials. Now, again, as we did before, you can look at the distribution of the rightmost fermion. Okay, so you ask at the distribution of this X max, and now because again you have a determinantal point process, this is again given by a Fredholm determinant, and what you get is that this is a Fredholm determinant, but given by this, I mean, expressed in terms of this new kernel, which has this Fermi factor in it. Okay, so that's a finite temperature generalization, if you want, of the Tracy-Widom distribution. Okay, so that's we were quite happy to have that because it's a nice generalization of it. But what we soon realized is that it turns out that this distribution, exactly the same distribution, actually happens in a completely different context, in the context of stochastic growth processes. And I will basically try to end up with this connect by showing you this connection. I will not show you all the details of the computations. They are relatively involved, but just tell you the result. So let's look at this model that has been widely studied in the last 20 years, which became extremely popular, which is this equation of motion for the height field. So imagine that you have a kind of Eden growth. So it's a kind of, you are growing, basically, you have a model basically that imagine a kind of tumor which is growing. Imagine that this is just an interface which is growing between, say, a stable phase and an unstable one, and you would like to understand the stochastic evolution of h of xt as a function of x, which is the radial coordinate here, and as a function of t. And you can argue that it's actually given by this Kardar-Parisi-Zhang equation here, which has three types of terms here. Here, this is simply the surface tension term, which you will know, which is linear in h. This eta here is really due, I mean, it's just a simple thermal noise. But now you have this non-trivial term here, which is due to the growth, which is due to the curvature, basically, and which really encodes for the nonlinearities of the growth process, and which is now proportional to dxh squared. And of course, because of the square here, the problem becomes quite complicated. And this, probably you have heard that there have been some beautiful experiments in the group of Takeyoshi and Sano on liquid crystals, and that's where I took this picture, where they were really able to measure this H here, and eventually compare that to theoretical predictions. Indeed, it turns out that due to quite remarkable progress, both in mathematics and in theoretical physics, it's actually possible to solve this equation under some for some initial conditions, and in particular for this type of growth or curved geometry, it is actually possible to compute explicitly the solution of the KPZ. And I just mentioned here several groups. It turns out that several groups provided a proof of these results using independent methods. And the result is that Okay, the object that you have to look at is a bit complicated. So if you look at h, so let's look at h at x equal to 0. So instead of looking at h, you look at the exponential of h. Well, the reason for that is that you probably know that there is a connection between the Kardar-Parisi-Zhang equation and the directed polymer model in a random environment. And exponential of h is just the partition function for this directed polymer. So it's not completely stupid. I mean, or at least it doesn't really come out completely out of the blue as why you would like to study that. But so you look at this quantity exponential of h, you need to rescale it a little bit, center it, and so on. And then you take the generating function of this object. And what is shown is that, what these people have shown, is that this quantity, this generating function, it can also be written as a Fredholm determinant. And it turns out that this, the kernel that you have here, which I call KPZ, you see it has a very similar structure as we had before. This is the product of these every functions times this Fermi factor here. Now, t to the 1/3 basically plays the role of the inverse temperature. So if you just look at what we had before in the free fermion problem, we had this, the distribution of the rightmost fermion, which was given by this Fredholm determinant. And now we get this generating function for the height field there. And this is exactly the same kernel where you see again that large time means B large, and B large means basically 0 temperature. Okay, so large time is like 0 temperature, while short time is like high temperature in the KPZ, in the free fermion problem, non-interacting fermion problem. You can give actually, so that's what I meant. You can basically give some probabilistic interpretation of behind that. Basically, it says that the fluctuations of the rightmost positions around the edge, they are up to some rescaling. They are equivalent to the height field in the KPZ plus an independent random variable, which is a Gumbel random variable. Now, this is very nice, but this is also for us, at least at the moment, and since now a few years, this actually remains a bit as a surprise and even a bit as a puzzle, because it's very hard to see any KPZ equation in the fermion problem. And at the moment, we don't have any clear interpretation behind that, but it's a quite remarkable connection between these two very rich problems. Okay, so yeah, if I had time, I could tell you what happens in higher dimension, but okay, I will just skip that and just go to the conclusion and just make a short summary of what I tried to tell you. So first, I try to show you that there is indeed a very rich and also quite universal edge physics for these trapped free fermions, which were unveiled using these random matrix tools, and more generally these determinantal point processes that we can show here. For instance, if you look at the simplest case of the harmonic potential, I've shown you that there is a very nice exact mapping at 0 temperature between the fermions and the Gaussian unitary ensemble of random matrices. Now, quite surprisingly, if you include temperature, we have shown that there is a quite non-trivial connection with stochastic growth model in the Kardar-Parisi-Zhang equation, and that's something quite, I mean, which remains quite puzzling. And it turns out that this actually has opened a kind of subject in the field of combinatorics. Now the people are talking about this finite temperature combinatorics. We were supposed to have a very nice workshop in Australia, but of course it has been cancelled. But there are a series of works, in particular by Dan Bettea and Jeremy Boutier, around these ideas. This is for the case of one dimension, but of course, I mean, I say of course, one can in principle also go to higher dimensions. There, you typically lose the connection to random matrix theory, except in some two-dimensional case, which I could elaborate more on. But in general, you lose the connection to RMT, but nevertheless, you still have determinants, right? You have fermions, you have non-interacting fermions, so you have Slater determinants. So that means that you have determinantal point processes, and with that, you can still do progress. Now, with these techniques, various things can be studied, and which some of them are actually quite useful from the experimental point of view. They concern, for instance, linear statistics. This has been done with one of our postdoc, Jacek Grela, already some years ago. Quite recently, we studied the full counting statistics also in connection with entanglement entropy for non-interacting fermions in higher dimensions too. And this was done more recently with our current postdoc, Naftali Smith. Now, this is about the statics. You may also, a very interesting question that you may ask concerns the Wigner function. Okay, so here I've been looking at what happens in the x coordinate, so in real space. And this is relevant also from the experimental point of view, because people are now really able to make this direct imaging of the fermions. But experimentally, people usually they prefer to measure what they call these time of flight experiments. So that means that they measure the momenta, okay, instead of real space. They prefer to measure what happens in Fourier space, if you want. And then it's quite reasonable and natural to ask about what happens in phase space in XP. Okay, so there is a nice formalism to study that, which is called this Wigner function, which we have studied in great detail with my collaborators, David Dean, Le Dussal, Pierre, and Satya Majumdar. And now, okay, I will just finish by that. As you probably know, I mean, there is also a quite, I mean, there are a lot of activities currently in the context of non-equilibrium quantum dynamics. And of course, these fermions are, in principle, can be studied, although they are not so easy to study. But okay, we already started to study that in these two papers, and there is certainly much more to do along these lines, since the methods and the models are actually extremely rich. Okay, so with that, I will thank you for your attention and stop here.
Okay, thank you very much, Gregory. Well, let's see whether there are questions.
Okay.
From our audience.
Sure.
From the YouTube channel.
Okay.
So maybe everything was very clear.
Yeah, okay. Yeah, I'm not sure. Maybe I was too fast. I don't know. Maybe I went a bit too fast.
Well, our students they are very shy usually. That's
okay,
the problem.
Okay. Yeah, I can imagine. Okay.
Well, I mean, I have really two questions, so it's not just to fill the time. So
okay, please.
One thing is these edge statistics. So as you talked about cold atoms, in which sense could they be experimentally checked, or could they be relevant? Well, maybe relevant. So for instance, can you imagine something about transport across trapped fermions or something like that?
Yeah. So this is So in principle, okay. Of course. So the main there are several principle maybe problems related to that, but okay. We already started to discuss with several groups. It's in principle okay. They seem to say that this edge statistics in principle should be observable, but there are some care to be taken. One of them indeed is the fact that typically if you look at what happens at the edge, it might be that usually these are fermions with a high momenta, and it might also be that they have badly thermalized, in the sense that it could well be that these fermions which are at the edge, maybe they have experienced less collisions with the other atoms, and in that sense maybe it's not completely obvious a priori that they would be described by equilibrium statistical physics as we did here.
Mhm.
So from that point of view, I mean, exploring really the equilibrium statistics is probably, I mean, can be problematic. Now, on the other hand, in principle, indeed, one could measure the. I mean, there was some. So from the dynamical point of view, indeed, we have some predictions for instance, the time correlations at the edge or these kind of things, which in principle could give some hint on the on what happens at the edge. But of course, this is, I mean, the answer is not so clear at the moment, and this is obviously an ongoing question, I would say.
Okay.
And if you have suggestions, I mean, I would be happy to hear.
Yeah. I was just thinking about that. The other question was is Coulomb potential.
Right.
What happens with that?
So you mean this Coulomb, this 1/r squared?
Yes, 1/r. Yeah.
Yeah. So yeah, so there indeed, I mean, the situation is different. So if you look at the local correlations there, what happens is that you fall into another universality class, which is not described by the Airy kernel, but by the Bessel kernel, which has been quite well studied also in the context of random matrix theory. This is what happens, for instance, if you look at the Laguerre or Wishart-Laguerre ensemble. And in these matrix models, you have a hard edge. So typically the density, if you look at in the language of RMT, you would have a density which is diverging like 1/square root of x close to the edge. And if you look at the boundaries, then, I mean, the local correlation, sorry, they will be given by the Bessel process. But in principle, you see, I mean, this is something that we have also quite well characterized.
But now I'm confused. I mean, it's the Coulomb potential, so there is no hard edge, right? I mean, I would have thought that there is no edge at all.
Okay, so you have in mind the true Coulomb potential in 3D, in 3D,
or in 1D, say, of course.
In 1D, if you take the 1/r, yes, indeed. So if you take the 1/r, okay, sorry, yes, 1/r is a kind of borderline case, for which, yes, you're right. In 1D, if you really take the 1/r, yes, indeed, what you will see is just the sine kernel, in fact.
Ah, okay.
Yeah, and
it makes sense. I mean, it really makes sense. Oh.
Yeah. In fact, it's a kind of borderline case in the sense that then if you go, I mean, if you have something which is diverging faster than 1/r, then you start to create an edge.
Mm-hmm.
But 1/r, indeed, you're right, that doesn't create, I mean, it's just a sine kernel in this case.
Ah, okay.
Yeah. Yeah, that's a good point.
Okay, thank you. Oh, nice. Well, then, no more questions. Last chance.
Okay.
Well, then, thank you very much.
Yeah, thank you to you.
And see you soon, hopefully.
Yeah.
And all the best to you. Let's
the same.
Hope to get over this corona pandemic.
Yeah, let's hope so. Yeah, thank you again.
Goodbye,
Okay.
Gregory.
Bye.